For rotating equipment to operate smoothly, its shafts have to be properly aligned. If the shafts are misaligned, bearings, seals, and couplings can wear excessively, leading to premature equipment failures. Mechanics are usually responsible for performing shaft alignments. In order to perform this job properly, you'll need to be familiar with the equipment, procedures, and techniques involved. In this program, we'll be discussing those aspects of shaft alignment. We'll be looking at a method of aligning shafts called the reverse dial method. The chances are your facility uses this method for some of its alignment work. We'll also discuss how to align vertically mounted equipment. And finally, we'll look at some other methods and equipment that can be used to measure misalignment and determine the necessary corrections. In this part of the program, we'll introduce the reverse dial method. Generally speaking, the reverse dial method is like other methods in that misalignment is measured and corrected. But before you can do that, there are a few preliminary steps to take care of, and that's what we'll do first. To understand the reverse dial method, it will help if we brush up on some alignment fundamentals. Before you can properly align two shafts, you need to determine the amount of misalignment. And as you may recall, there are two main types of misalignment, parallel and angular. In addition, you'll often find that both types of misalignment can be present in both the vertical and horizontal planes. As illustrated here, parallel misalignment means that the two shafts are offset. Their center lines aren't collinear, but they are parallel. It's this offset that has to be measured to determine how much parallel misalignment is present. Angular misalignment means that the center lines of the two shafts intersect at an angle. The gap between the two hubs is larger on one side than on the opposite side. The difference in the gap between the two sides has to be measured to determine how much angular misalignment is present. One way of measuring misalignment is the reverse dial method, which is set up here. In this example, there's a pump and a motor. For this job, the motor will be moved to align its shaft with the pump's shaft. So the motor is the movable component and the pump is the fixed component. When you do an alignment, you need to establish an orientation and then stick with it throughout the alignment procedure. The orientation is typically set up with the fixed component on the left and the movable component on the right. With the fixed component on your left, clock face marks are established on the fixed component's hub. The reverse dial method uses brackets and dial indicators. One bracket is mounted on the movable component's shaft. Attached to this bracket is a dial indicator whose stem contacts another bracket. The stem touches a smooth, flat part of the bracket called a target. This target represents the rim of the fixed component's hub. Since this dial indicator is near the fixed component, we'll be referring to this as the F dial indicator. The other bracket is mounted on the fixed component's shaft. This bracket also has a dial indicator attached to it. However, the stem of this dial indicator contacts a target area on the first bracket. This target represents the rim of the movable component's hub. We'll refer to this as the M dial indicator because it's near the movable component. With the reverse dial method, rim measurements are used to correct parallel and angular misalignment in both the vertical and horizontal planes. We'll see how that's done later in the program when we work through an example. Like other methods of shaft alignment, the reverse dial method requires that any preparations be done before taking dial indicator readings. For example, the shafts of both components are often smoothed with crocus cloth to remove any burrs or blemishes that can cause the brackets to rock or slip out of position. There are several preparations normally done for an alignment job. You'll find a checklist of the major ones in your text. But one preparation that's especially important for reverse dial alignment is measuring bar sag. The bars that the dial indicators are attached to have a tendency to deflect or sag. To get accurate dial indicator readings, this bar sag has to be taken into account. Also, since there are two bars involved in the reverse dial method, the bar sag will have to be measured for both. One way of measuring bar sag is to use a test fixture or a piece of pipe. But if you do, the brackets and dial indicators should be mounted on the test fixture as close as possible to the way they'll be mounted on the pump and motor shafts. This should give you precise readings. To determine bar sag, first the mechanic measures the distance between the two brackets as they're attached to the shafts. Then he marks the shaft so he'll know where to mount the brackets later. He's attached the brackets to the test fixture, so the distance between them is the same as it was on the shafts. Since he's going to measure the sag for both bars, both dial indicators have to be zeroed. Next, he rotates the test fixture 180 degrees. Finally, he takes readings from the indicators and records the values on a data sheet. The bar sag values are obtained by dividing the actual readings on the dial indicator by 2. Dividing by 2 accounts for the sag that was negated by zeroing the indicators. In this case, the reading for the F dial indicator is -2 mils. So the bar sag is -2 divided by 2, or -1 mil. The F indicator bar sag is a negative value because as the dial is moved from 12 o'clock down to 6 o'clock, the bar sags and pulls the indicator away from its target, which causes the indicator stem to move outward. With a balanced type dial indicator, outward movement of the stem produces a negative or minus reading. The M indicator reading is +2 mils. Again, we divide by 2, so the bar sag is +1 mil. The M dial indicator has a positive bar sag value because as the bar is moved from 6 o'clock up to 12 o'clock, the sagging bar pushes the stem inward, producing a plus reading. As we said earlier, the bar sag information will need to be recorded on a data sheet. Now, the data sheet we'll be using for the reverse dial indicator method may look a bit different from the one used in your plant, but chances are they contain the same information. You'll see a place to include specific information about the equipment you're working on, such as the operating RPM of the motor, the alignment tolerance, and the amount of thermal growth associated with the pump and motor. For this example, the thermal growth characteristics are the same for the pump and motor, so thermal growth will not be a factor in the alignment. There's also a place on the data sheet for tape measurements, and there's a place to record dial indicator readings. The F represents the fixed component, and the M represents the movable component. The 12 o'clock, 3 o'clock, 6 o'clock, and 9 o'clock positions correspond to points where readings are taken. This section is where the final readings are recorded. As indicated on the data sheet, another step that's required for a reverse dial alignment procedure is taking the appropriate tape measurements. Typically, 3 measurements are needed. For our example, the first measurement is the horizontal distance between the stems of the 2 dial indicators. The second measurement is the distance between the F dial indicator stem and the center line of the support bolt for the movable component's inboard foot. And the third measurement is the distance between the F dial indicator stem and the center line of the support bolt for the movable component's outboard foot. Now, these measurements need to be as accurate as a tape measure will allow. You'll notice that these measurements are made parallel to the shafts. The measurements should be recorded on the data sheet. The first measurement is labeled D1. In this example, it's 6 inches. The second measurement is labeled D2, which is 12 inches. And the last measurement is labeled D3, and it's 24 inches. At this point in our procedure, we've installed the brackets and dial indicators. We've done the pre-alignment preparations, and we've taken our tape measurements. The next step is to take a set of readings with the dial indicators. We'll be doing that in the next part of the program. For now, though, take some time to review the material we've just covered in your text. Clear up any questions you have before continuing. In the last part of the program, we began an alignment job using the reverse dial method. The equipment was installed, the preparations were done, and the tape measurements were taken. The next step is to measure the misalignment between the two shafts and correct it. Now, it's possible to measure misalignment in both the vertical and horizontal planes and then correct all the misalignment at one time. If you do this, however, you could accidentally shift the movable component in the horizontal plane while you're correcting vertical plane misalignment. This will make your adjustments inaccurate. To minimize this possibility, many mechanics find it easier to align one plane at a time. That's what we're going to do here. We'll do the vertical plane first, then in the next part of the program, we'll measure and correct the misalignment in the horizontal plane. The procedure we'll follow begins with the F dial indicator at 12 o'clock and the M dial indicator at 6 o'clock. Next, the face of each dial indicator is adjusted to read 0 and tightened into place. Before taking vertical plane readings, the shafts are rotated a full 360 degrees and the dial indicators are rechecked for 0 readings. If either indicator didn't read 0, it's possible a bracket may have slipped. He'd then have to check the brackets and indicators and redo this step. Now, there are a few things you should keep in mind when you're rotating shafts with dial indicators on them. For one, don't use the brackets as handles to turn the shafts. The brackets could slip out of position. Also, you should rotate the shafts in only one direction, which should be the direction of rotation during normal operation. This means that you should bring the dials to the read point, whether it's 12, 3, 6, or 9 o'clock, without rotating back to it. If you go past the read point, go all the way around again in the same direction. The reason for this is that there may be enough play in the bearings to throw off your readings if you back up to the read point. The mechanic found that both dial indicators still read 0. So he takes the vertical plane readings by rotating the shafts 180 degrees until the F dial indicator is at 6 o'clock and the M dial indicator is at 12 o'clock. Then he'll take readings from both dial indicators and record them on the data sheet. In this case, the reading on the F dial indicator is -6 mils. With a balanced type dial indicator, you need to watch which way the needle moves so you interpret the sign of the reading correctly. The reading on the M dial indicator is -16 mils. Now the mechanic takes another set of readings to make sure the first set is accurate. If the second set of readings isn't the same as the first, it means that something has shifted, and he'd have to retighten the brackets and start over. In this case, the readings are the same, so everything seems to be in order. On the data sheet, the F indicator reading at the 6 o'clock position is recorded here. This reading by itself is not enough to determine the vertical misalignment. We have to do some math. We see that this reading is divided by 2. This accounts for misalignment that was negated when the dial indicator was zeroed. -6 divided by 2 equals -3. We also have to account for the bar sag we measured earlier. We have to subtract the bar sag value. -3 minus -1 equals -2. Remember that subtracting a negative number is the same as adding a positive number. This value is recorded in the box labeled FV. FV represents the amount of vertical misalignment measured by the F dial indicator. The reading on the M dial indicator is recorded here at the 12 o'clock position. Then we have to do the same calculations as before. -16 divided by 2 equals -8. Then, subtracting bar sag, -8 minus +1 equals -9. That value gets recorded in the box labeled MV. MV is the amount of vertical misalignment measured by the M dial indicator. At this point, we've obtained a complete set of vertical plane readings on the data sheet. The next step is to convert these readings into information that will tell us how much to move the motor to correct the misalignment. There are a couple of ways to do this. One way is to use formulas and calculate the required movements mathematically. That way is explained in your text. What we're going to do here is figure out how to correct the vertical misalignment by plotting a graph. Although the increments on the graph paper can have any value, the vertical markings on this graph will represent increments of 1 mil. The horizontal markings will represent increments of 1 inch. The first thing we'll do is plot a base point near the left side of the graph. We'll label this point F because, as we'll see, we'll use this point to plot values obtained from the F dial indicator. Next, we'll draw a straight line across from point F. This line represents the center line of the fixed component's shaft. Now we need to get some information from the data sheet. The first value we'll need is D1, which is 6 inches. As you recall, D1 is the distance between the stems of the two dial indicators. To plot this value on the graph, we'll start at point F and count over the value of D1. Since the horizontal markings are in 1-inch units, we have to move over 6 increments. We'll mark a point here and label it M. We'll use this point to plot values obtained from the M dial indicator. The next value we have to plot is D2, which is 12 inches. D2 is the distance between the stem of the F dial indicator and the center line of the support bolt for the inboard foot of the motor. To plot this value on the graph, we start at point F, then move along the line 12 increments, and place a point we'll label X. The next value we need from the data sheet is D3, which is 24 inches. D3 is the distance between the stem of the F dial indicator and the center line of the support bolt for the outboard foot of the motor. To plot this point, we'll start at point F again. This time we'll move along the line 24 increments and place a point we'll label Y. To continue, we'll need the value of FV from the data sheet. FV, which is the vertical misalignment measured by the F dial indicator, is -2. Now we need to plot this value on our graph. We'll start at point F. If FV were a positive value, we would move up from point F to plot it. But FV is negative, so we'll have to move down from point F, 2 increments. We place a point and label it FV. Next, we'll need the value of MV, the amount of vertical misalignment measured by the M dial indicator. MV is -9. To plot MV on the graph, we'll start at point M. Since MV is -9, we move down 9 increments and place a point labeled MV. Now we'll draw a straight line that intersects points FV and MV. This line represents the center line of the movable component's shaft. Since the movable component is aligned to the fixed component, this line also represents the amount of misalignment in the vertical plane. To determine how much the motor must be moved to correct the misalignment, we'll follow straight down from point X to the line we just drew and place a point labeled XV. Next, we'll do the same thing from point Y. We'll label this point YV. If we count the number of increments between points X and XV, we'll know how far to move the inboard feet of the motor. In this case, the inboard feet must be raised 16 mils. By counting the number of increments between points Y and YV, we'll know how far to move the outboard feet. The outboard feet should be raised 30 mils. Correcting for misalignment in the vertical plane involves adding or removing shims under the feet of the movable component. In this example, since the motor has to be raised, shims will be added. The mechanic has the shim sizes he needs. The size is usually stamped on the shim, but it's still a good idea to measure the thickness with a micrometer to double-check the accuracy. When the proper shim packs have been determined, the motor's support bolts are loosened and the shims installed. Lifting the motor with a pry bar allows the shims to slide easily under the motor foot. When you're adding shims, it's best to use as few shims as possible. A stack of several shims could shift or flex and cause misalignment. When the shim packs are in place, the mechanic retightens the support bolts. At this point in the procedure, the misalignment in the vertical plane has been corrected. In the example we just saw, thermal growth was not a factor in correcting the misalignment in the vertical plane, but you'll often find it is. In your text, there's an example that shows you how to account for thermal growth. In this part of the program, we've seen how to measure and correct misalignment in the vertical plane. That's only half the job. You also have to measure and correct for misalignment in the horizontal plane. We'll see how that's done when we come back. In this part of the program, we're going to continue and complete the alignment job we've been working on. We've measured and corrected for vertical plane misalignment. Now we're going to do the same for misalignment in the horizontal plane. As before, we'll take dial indicator readings, record them on a data sheet, plot a graph representing the misalignment, and then make the required moves. As you recall, we're using the reverse dial method. This is the F dial indicator, and this is the M dial indicator. Also, we had established our orientation with the fixed component on the left, the movable component on the right. The clock face positions are on the fixed component's hub. This is 12 o'clock, 3, 6, and 9 o'clock. For these measurements, the mechanic will zero the F dial indicator at the 3 o'clock position and the M dial indicator at the 9 o'clock position. Next, he rotates the shafts 360 degrees to make sure the indicators still read 0. They do, so he's ready to take his readings for the horizontal plane. He rotates the shafts 180 degrees, so the F indicator is at 9 o'clock and the M indicator is at 3 o'clock. The F indicator reads plus 40 mils. A mirror gives a reverse image, so he's careful to interpret the reading and sign correctly. The M indicator reads plus 48 mils. These readings are recorded on the data sheet. On the data sheet, the F indicator reading is recorded here. This reading is divided by 2, so plus 40 divided by 2 equals plus 20. This value is recorded in the box labeled FH, which represents the amount of horizontal misalignment measured by the F dial indicator. You'll notice on the data sheet that bar sag is not subtracted in this case. Bar sag is not a factor in measuring for misalignment in the horizontal plane. The M dial indicator reading is recorded here. This reading is also divided by 2. The result, plus 24, is recorded in the box labeled MH. This represents the amount of horizontal misalignment measured by the M dial indicator. The mechanic is taking a second set of readings to confirm that his first set was accurate. The two sets of readings match, so the mechanic can go on and determine how to correct the misalignment. After taking the readings, the next step is to convert these readings into information that will show us how to correct the horizontal misalignment. To do that, we can use formulas, which are explained in your text, or we can plot a graph, as we did for the vertical plane. We start with point F, which will be used to plot values obtained from the F dial indicator. Then we draw a straight line across from F. Now we'll plot the tape measurement values from the data sheet. D1, the distance between the stems of the two dial indicators, is 6 inches. We count 6 increments from F and label this point M. M will be used to plot values obtained from the M dial indicator. The next value to plot is D2, the distance between the stem of the F dial indicator and the center line of the support bolt for the motor's inboard foot. D2 is 12 inches. We count off 12 increments from F and label this point X. The last tape measurement is D3, the distance between the stem of the F dial indicator and the center line of the support bolt for the motor's outboard foot. D3 is 24 inches. We count off 24 increments and label this point Y. This line represents the center line of the fixed component's shaft. Now we need the values of FH and MH from the data sheet. We start with FH, the horizontal misalignment measured by the F dial indicator. FH is plus 20 mils. To plot FH on the graph, we start at point F, and since FH is positive, we move up 20 increments. We label this point FH. Next, we need the value of MH, which is the horizontal misalignment measured by the M dial indicator. MH is plus 24 mils. To plot this point on the graph, we start at point M and count up 24 increments. We label this point MH. Now we'll draw a straight line through points FH and MH. This line represents the center line of the movable component's shaft, and therefore the misalignment in the horizontal plane. To determine how far the motor must be moved to correct the misalignment, we'll follow straight up from point X to the line we just drew and place a point labeled XH. Next, we move up from point Y to the line and label this point YH. At this stage, we can determine how to move the motor by counting the increments between X and XH and between Y and YH.